Hey there, organickers! Today I want to talk about how we can separate organic molecules on the basis of their acidity. So I have here three organic molecules, and they have different functional groups. And you've seen at least one of these molecules before, and I know that you've heard of all of these. We have menthol, flavor ingredient in peppermint. We have acetyl salicylic acid, or aspirin, and we have nicotine. Three organic molecules having different functional groups. Let's go ahead and add in our lone pairs of electrons, because if you want to identify basic sites, that's what you need to look for, are lone pairs of electrons that can be donated to an electron deficient species, or to a Lewis acid. Here we have a separatory funnel, and you may have used this in your labs. And I have an organic phase and I have an aqueous phase. So say my organic phase is cyclohexane. Cyclohexane is going to be on the top because it is less dense than water. Most of the time your organic phase will be on the top. There are some organic solvents that will be on the bottom. Those are the halogenated solvents, usually chloroform and methylene chloride. So say on the bottom I have a solution of 10% hydrochloric acid in water. I'm going to have an acid-base reaction taking place between HCl and water. So HCl will donate a proton to H2O to give me hydronium ion and Cl-. If I consider the pKa's of my two acids, on the right we have hydronium ion with a pKa of 1.7. On the left we have HCl with a pKa of -8. And remember that you're always going to go towards the side of the weaker acid, so towards the side of the larger pKa. So my equilibrium is going to lie far to the right. This is actually a phenomenon that we call the leveling effect. And what the leveling effect says is that you cannot have an acid in water that is stronger than hydronium ion, or H3O. And the reason is, any acid that's stronger than H3O will react with the water to produce H3O. So all of my HCl is going to react with water to give me hydronium ion. What will happen with my three organic molecules in the presence of H3O, or hydronium ion? I could have an acid-base reaction taking place. And if we look at nicotine, we can see two lone pairs of electrons, so we have two potentially basic sites there where a proton might go. So my first reaction, I'm protonating the sp3 hybridized nitrogen. Let's look at our relative pKa's. I've already told you the pKa of the hydronium ion is -1.7. The pKa of the secondary nitrogen, somewhere around 10 to 11. We'll just say 11 for argument's sake. Remember that our equilibrium will always lie on the side of the weaker acid and the weaker base. My equilibrium will lie on the side of the protonated nitrogen. How about our other nitrogen? Let's look at our relative pKa's. Again, hydronium ion is -1.7, and the pyridinium ion has a pKa of 5.2. So again, my equilibrium is going to lie to the right. So I'm going to protonate probably both of those nitrogens. What about methanol? Here's the acid-base reaction that I can write. Remember that you look for lone pairs of electrons, and those are going to be your basic sites. You'll also remember that alcohols can be amphoteric, but in this case, we're reacting our alcohol with a strong acid, so our alcohol is going to behave like the base. It's going to give me my protonated alcohol, which we also call an oxonium ion. And let's look at our pKa's. H3O, hydronium ion, -1.7 versus -2.5 for my oxonium ion. This time my equilibrium is going to lie to the left. Remember, I'm going to lie on the side of the weaker acid, and the weaker acid has the larger pKa. So nothing's going to happen to menthol. Let's look at acetyl salicylic acid, or aspirin. There are lots of potentially basic sites here in this molecule. Let's look at each one of them one at a time. First, for protonation of a carbonyl, and this could be either one of those carbonyl groups, we have a pKa of about -6. My equilibrium is going to lie again to the left, so we're not going to protonate those carbonyl groups. For my sp3 hybridized oxygen on the carboxylic acid, my pKa is about -2.5. So again, my equilibrium is going to lie to the left. How about that ester oxygen? Well, here my pKa is -3.8. So it's smaller than the pKa of hydronium ion. So again, my equilibrium lies to the left. So acetylsalicylic acid is not going to be protonated by H3O. In our two-phase mixture of cyclohexane and 10% aqueous HCl, we're going to have menthol, acetylsalicylic acid, neither one of which will be protonated, and we're going to have our protonated pyridinium ion, our protonated secondary amine, and probably we're going to have some doubly charged species as well. So where are these compounds going to go? In my cyclohexane, which is an organic solvent, I'm going to have all of my uncharged species. My menthol and my aspirin will go to the cyclohexane. In my aqueous phase, I'm going to have my charged species. So my protonated nicotine will be in the aqueous phase. And remember that those counterions, the chloride anions, are going to go along with the nicotine. So even though these are mid-sized organic molecules, when you can introduce a charge to these organic molecules, that will make them water soluble, because now they have an ionic bond, the ionic bond between the positively charged nitrogen and the negatively charged chloride in this case. Now we've managed to pull out the nicotine from this mixture of three organic compounds. Where do we go from here? Let's drain off the aqueous phase, and then let's take our cyclohexane, which contains the menthol and the aspirin, and let's add to that 10% sodium hydroxide. Again, the cyclohexane, being less dense than water, is going to be on the top. Well, what's going to happen with our menthol? I have hydroxide anion. My alcohol could act like an acid, and hydroxide could pull off a proton. Let's look at the pKa's of our conjugate acids. The pKa of water is 15.7, whereas the pKa of menthol is 17. Remember that we're going to lie on the side of the weaker acid and weaker base, so that's going to be on the left. So nothing's going to happen to my menthol. Let's look at our acetylsalicylic acid. We have one potentially acidic proton here. It's the proton on the carboxylic acid. Remember, you're never going to pull off a proton from a carbon with another base, because there is no base strong enough to do that. So the only proton that's available is the one on the oxygen. And let's consider our relative pKa's. Water, again, 15.7. Our acetylsalicylic acid has a pKa of 4.2. Remember that we lie on the side of the weaker acid and the weaker base, and the weaker acid has the largest pKa, so that's going to be on the right. So my acetylsalicylic acid is going to be deprotonated and converted into an anion. So now what I'm going to have is neutral menthol and negatively charged carboxylate anion, or a negatively charged benzoic acid derivative. Where are they going to go? My neutral species, menthol, will go into the cyclohexane. My negatively charged species, the acetylsalicylic acid, which is deprotonated, will go into the aqueous phase. So now I've managed to separate my three organic molecules on the basis of pH. And remember that the counterion is just going to go along with the carboxylate anion. So let's just look at a summary of what we've done. Starting with a mixture of three organic molecules, we partitioned that between cyclohexane and 10% HCl. Our basic or nitrogenous species reacted with the hydronium ion that was formed to give us positively charged species, which went into the aqueous phase, of course along with the chloride counterion, and our neutral species stayed in the cyclohexane. Then we partitioned between cyclohexane and 10% sodium hydroxide, Our acidic species were converted to the conjugate base, or the carboxylate anion. Making this anionic also made it water soluble. And the menthol, which didn't react at all, stayed into the cyclohexane. So there's the summary of how you can separate organic molecules on the basis of their acidity.